So now that we have an understanding of how instructions could get encoded and stored in the memory of a computer, we need to address a related problem which is called compilation. Right? So those of you who have done some programming before would probably recognize what's on the left as a small C program. The rest of you will be writing a lot of these programs as we proceed, right? And the important thing that I want to sort of bring out over here is the fact that this chunk of text that you see over here, right, is a program, but there are a few things about it that are important to observe and understand. One of them is, as you can imagine, this program is meant to be human readable, right? Now I am going to be using a computer to actually type in the program. That's a different story. That makes it machine readable or computer readable at some level, right? But at this point the computer is literally only sort of manipulating characters on the screen, right? It doesn't actually have the ability to run this program and do something useful with it. Okay, this format or this particular variant of the program is very much meant for human consumption, for people to read, understand, edit, modify and so on. Okay. Now a couple of things to keep in mind, of course, the colors that you see here, the fact that this is in green, the fact that this is in brown, there are some things in red, white, and there's a background out there which is dark. All of those just happen to be my preferences as set by the editor that I used for editing this particular code, right? They are not part of the program, so you could change those colors and nothing changes in the program. Now that's something actually interesting, because there have been some programming languages that actually tried to make use of things like color, right, in order to indicate the nature of certain parts of a particular program, right? But most programming languages don't, and C in particular does not. Now a similar thing, the next thing you will notice is, there are these brackets, right, the curly braces starting and ending here. That seems clear enough, right? It's sort of encasing things into a block, and whatever is in between those is a chunk of text that we are trying to interpret in some way. But then you will notice that there are these big gaps before the actual text itself starts. This is usually called indentation, right? In the case of a programming language like C, that indentation is not relevant. I could have squeezed all this together and left no spaces in between them and still it would work, right? But in other languages such as Python, right, the most famous of them, indentation is mandatory, and that is in fact what determines the start and end of different blocks in the program, right? It's an interesting choice. I mean, until sort of Python made that popular, that was a very limited kind of usage that people had in very specific kinds of languages. Mostly people did not want the language to be indentation dependent, okay? But the bottom line is, as far as we are concerned, this text out here is what really matters. That's what contains the gist of the program. Now all of this is in turn organized into what we call files, right? You might be familiar with files as just any document. So for example, if you have used a word processing system such as Microsoft Word or Google Docs, you will know that there are word processing systems which literally allow you to type, right? You can type letters, you can type documents, you can type reports, you can highlight certain parts of the text, make them bold, make them larger font, mark them as headings, right? Emphasize some of them, make them bold, convert them, some of them into italics for some other kinds of emphasis and so on, right? That's a word processor. Effectively what the word processor is doing is working or manipulating text which has been encoded in some way, and finally saving it in the form of a file, right, that you can always come back to later. In our case, we are going to be using these files in order to store the actual programs that we want to write and make the computer execute, okay? So these files essentially, as far as we are concerned, they help us to organize text in a human readable form, but they are organized in such a way that they can be manipulated by computers, right? So at this point in time, I have all of this text in a format that is inside a computer. Of course, right now you are seeing something on the screen. which naturally means it is inside the computer, but it is in a very strange format. It's basically there as an image, right? A computer cannot directly take this image and do anything useful with it. On the other hand, if I actually typed it in as text into a file, then it's possible that a computer could do something else with it, which is manipulate it, convert it into some other format, okay? And that is sort of what we want to do. We want to start off with a format which is human readable, and from there go to something that is computer interpretable. So effectively, in other words, this compilation takes care of that problem, right? What it says is, I have a program that is in a human readable format, it's some kind of a file, okay? And what I want to do is transform the text that I wrote somehow into a machine interpretable format, okay? Compilation is essentially this process. How do I go from here to here, from left to right? Okay, what it says is, you start off with something that's human readable, which could be inside a computer, but the point is, at that stage, it is the computer can process it as text, but doesn't yet know how to actually execute the instructions or do anything useful with the program. Compilation is that process that takes the text that you wrote and converts it into something that the machine can run or execute. Okay. So for that, the model that we use, as we have been doing all this while, is that there is a certain amount of memory available to us. I have just put in some blocks out here saying that yes, these are just some arbitrary divisions within the memory, and there is a CPU whose job is basically to communicate with that memory, right, and do something useful with what is stored inside. So I am going to take that memory, and what I am going to do is take some chunk of it, right, some part of the memory, and take my program, right, the program that you saw out here, right, encode it into a set of numbers and put it into that part of memory. So effectively what I am saying, in other words, is all of these blocks of bits that we have over here correspond to the encoding of the program that I started with. So this input program, in other words, is data as far as my compiler is concerned, right? What is the compiler? It's a program that takes data as input, produces data as output, okay? So the compiler, since it's a program, can itself sit in the memory of the processor somewhere else, right? Obviously not in exactly the same place as where the data is, but they could overlap to some extent, as long as one is not sort of deleting the other or like overwriting it with something else, okay? So this compiler, I am going to assume, has been magically created by someone previously, right? And this question of who created it, how did they create it, is a tricky one, okay? You might sort of have a clue already. After all, at the end of the day, what is this code? A set of numbers. So in the worst case scenario, somebody just has to sit down and actually write all those numbers out, right? They do it by hand, they do the compilation by hand, they look at each instruction in the program that you have, convert it into a corresponding set of machine instructions, convert it into a set of numbers and load that in here, okay? I could also have done that with any program, I could do that with any human readable program. What we are trying to do is find a shortcut. Say that rather than repeatedly doing this business of sitting with machine readable or human readable programs and trying to convert them into machine interpretable forms, I want to have one program that can do this cleverly for me. It can actually take in another input program and modify it to generate output. So in other words, the compiler goes into the CPU. How does it go into the CPU? The CPU has the program counter, remember, which sends an address into memory, or rather is a counter which tells me which instruction that I am looking at. All that I need to do is take that program counter and treat it as an address into this memory, get back corresponding instructions and execute those instructions one by one, right? So this part of it has already an executable program created by someone else. What the CPU will do is read in those instructions in turn will say, okay, fetch data from this part of the memory, which I know is where a program is stored, and will finally generate new output, What is that new output? That is getting stored into another part of memory, and this interesting, the interesting observation here is this new output is actually once again data corresponding to this program, which is why I am calling it data 1, but at the same time it is also the code or the machine instructions corresponding to another program, a new one that I have created. Okay. So this chunk of memory out here serves two purposes. It is being generated as output from this data by running this program, and at the same time it is also a new program that can run on its own. Okay. How would I run it? If at some point my program counter is changed so that it basically starts pointing to some part out here, I would start executing instructions that are sitting in this part of memory, which means I would be executing code 2. Okay. So what I have shown over here, once again, right, it will probably make a lot more sense for you to understand this by coming back to it later, right. What I mean by that is, right now it may look like just a very dense set of numbers and lot of gibberish on the screen that you don't really know how to make sense of, right. I will try and explain what these things are and why they are sort of useful for you to know about, but after you have written a few programs, and especially once you start looking at how different programs interact with each other, and you come back and look at this will probably make a lot more sense, right. It will be much easier to understand rather. Okay. So please keep that in mind, come back to it later once you have a little more experience with programming, but in the meantime take a look at it at a high level and try and appreciate the different parts of what we are seeing out here, right. What I have put on screen at this point is essentially the disassembled output from a program that I wrote. Which program? This one out here, right. So what I have done is I took this through a compiler. What did that compiler do? It transformed that into a machine interpretable form, right. The machine interpretable form is a set of numbers, and what I have out here is these numbers, right, and also a little bit of explanation of what each of those numbers corresponds to, right. So what this is showing, in other words, is that these lines, for example, that you see out here are essentially what we would call annotated source code, right. It's the actual code that we gave as input, but with some annotations that help to make it to tell us which part of the program corresponds to which part of the numbers that we have generated. Okay. Like I said, the important part is of course this block out here, right, the numbers themselves, and what we are trying to see is, do those sort of make sense in terms of the instruction sets and so on that we know exist inside the computer. These values that I have circled out here, right, so this 00, right, 8 zeros, which is basically a 32-bit value with the value 0, right, and these other numbers below it 0, 4, 8, C and so on are effectively the memory locations, the address offsets of the generated assembly code. What do I mean by address offset? This instruction out here, right, which is an add immediate instruction with this code FE010113 is at address offset 0. What that means is, when the computer starts to execute this program, what will happen is the program counter will first take this value 0 and will get to this particular location. It will see whatever is the instruction out there and execute it. In this case, that happens to be an add immediate instruction. Okay. The next instruction is at offset 4. Why 4 and not 1? Because it's 4 bytes. It's a 32-bit value which is 4 bytes. Therefore, the memory offset is 4, right. Once again, by convention, memory is usually addressed in terms of bytes, even though we normally try and get data out in terms of 32-bit words or 64-bit words. By convention, when someone says a memory location, its address, that is given as a address of a specific byte. Okay. So location number 4 contains yet another instruction, right, 00812E23, which if I looked at this number it would make no sense at all to me, but the disassembly tells me that that's actually a store word instruction. Now I am not going to go into why these instructions came about, or how they came about, or how they in fact implement whatever I wanted, except to point out a couple of sort of useful observations that are that can help us to understand what's going on, right. Let's look at this instruction out here, for example, right, at offset number C. What it says is, the code number corresponding to it is FA042423, but if you look at the annotated part just above it, it says that corresponds to sum equal to 0. Okay, and this instruction, the details out here on the right, essentially say I am going to take the value x0, which is the value 0 itself, and store it into a memory location mem of x8 minus 24. Why this x8 minus 24 and so on, right now just ignore it. The important point is it's a location in memory. And what is important over here is that sum has now got a specific location in the memory of the computer. And what have I done? I have initialized it to the value 0. Okay. So that is one place where, for example, you can directly look at the input code that we wanted, right, the human understandable code, and see how that translates into something that a computer can make sense of. Now if you look carefully at this, you will realize that what started off as human readable rapidly became one whole set of different numbers, and this is really difficult for a human to understand at this point, right. And that is pretty much the point. That's exactly why compilers are needed. If you needed to do all of this by hand each and every time, it would be extremely painful. It's not impossible. People have done like huge amounts of assembly language or direct machine coding even, right, but understanding and keeping track of it is very, very hard. The larger the program gets, the more and more difficult it becomes, which is why the compiler sort of takes care of that for you. It allows you to write the program in something that is easier for humans to understand, and then takes care of converting that into something that the computer can understand. Now similarly, there is a set of instructions out here, right, and it's worth sort of spending a moment on this, because it says at the top that the instruction is sum is equal to sum plus I, right. How does that get implemented? You can see that there is one load word out here, which if you look at it basically is the equivalent of load the value sum into the register x14. Okay. The next one is also a load, which basically says load I into x15. What is I? That's used to keep track of how many times you have run through this. It turns out that was also given a memory location to be stored in this case, right. And then add, of course, right, we expect sum plus I, right. So I add the two together, x14 and x15, and the result goes back into x15. And finally I need to update that, right, sum is equal to sum plus I. So I take whatever was in x15 and do a store back into the location where sum was. So the reason I brought this out was because when you look at snippets of assembly code, at first glance it looks completely incomprehensible, right. You can't make out what's going on. There are just so many numbers and so many assembly mnemonics and a bunch of other things out there. But when you look closely, you realize that a large part of it can just be ignored, right. You can pretty much dismiss most of it as being not directly relevant to the understanding of the program, at least, right. They are necessary, they are sort of housekeeping that the CPU is doing internally. The relevant parts should usually be things that you can actually pick up from the assembly code itself. Okay. And yet another interesting instruction, right. What we are doing over here is we take the value of I, load it into x14, take x15 and put the value 9 into it, right. So this add immediate 0 with 9 and put it into x15 is as good as taking the value 9 and putting it into x15. And then what I say is compare x15 and x14, and as long as it's less than or equal, right, jump back to L3, that is to say this memory location 018. Okay. So I would strongly encourage you as we move forward to not dismiss the idea of actually going and understanding a little bit about what the assembly code looks like, right? For those of you who are primarily going to be programming at high levels, let's say Python and similar languages, you don't need to know too much of this. Having said that, it helps because it tells you what your processor is actually capable of, right? For others, right, who actually want to get into embedded systems programming and so on, this is essential, right? You really need to get into the habit of looking at assembly code at some level and sort of figuring out what the different parts are doing. Very rarely will you need to write assembly code or machine code of your own, but it should be possible for you to look at it and sort of say, okay, this is what I think it's doing, right, and debug it if necessary. So compilation, right, to summarize, essentially what happens over here is that it takes human readable programs and converts it into machine interpretable code. There are many steps involved, right? The first would be what's called a syntax check, where we basically check whether what has been written by the human being even makes sense, so to say, right? The next step would be to map statements in that into equivalent code. So if I have something to add two numbers, for example, I know what kind of code is likely to get generated. If there's a comparison, I know that it's going to be some kind of a branch, right? And so on, right? And I'm obviously oversimplifying over here, but there are many steps that can be performed with varying degrees of complexity. And finally, the most important one, of course, is to generate actual machine code, right? That should be the output of the compiler. Now, in addition to all of this, most compilers also implement certain kinds of optimizations. What I mean by optimizations is that they perform modifications or they change the generated machine code in ways that improve the performance of the system in certain ways, right? What do I mean by improve the performance? Maybe I want my final program to run faster. How could I do that? If I could use 2 instructions to do the job of 3, right, then maybe I might be able to cut down on 1 instruction and thereby make it faster. There might be certain ways in which maybe using one particular kind of instruction turns out to be a faster way of performing a computation than another one. There may be other optimizations where when you look at a whole bunch of instructions together, you find that hey, they could all be replaced by something much simpler, right? There are clearly, this is not a trivial job, right, but there's a lot of research in compilers that basically results in a lot of improvements and a lot of optimizations that can be done. Right? One thing to keep in mind is a lot of what happens in compilers can be CPU dependent, right, which means that the kind of modifications you make are sort of dependent on the kind of processor that you are finally targeting as well. Right? So to summarize all of this, basically the compilation process is an essential part of taking your input code and converting it into something that the machine can run. Right? And understanding a little bit about that process will help you to write better programs.